Well, at least I can. Okay.
Okay, good.
Let me just introduce you. So it's my pleasure to introduce my former master's advisor, Professor Gordon Semenoff from the University of British Columbia. So Professor, please take it away.
Okay, thank you very much, Daniel. And I do very much appreciate the invitation to speak here. I'm sitting here looking out the window at a very heavy winter rain storm in Vancouver and wishing I was in Mexico. But unfortunately not. I'm sitting here doing this online, something we've gotten kind of accustomed to in the last few years. So I come to this field of science from maybe a slightly different direction than what I anticipate is so for most of the audience, in that I'm a field theorist and I'm interested in quantum field theory phenomena. And my interest in Dirac materials stems from that, in simply looking for contexts where things that we study all the time in quantum field theory might have, first of all, a physical application, or might simply have some context where we could actually understand them better, get feedback on the field theory. And so that's going to be, in a sense, the theme of what I'm going to talk about. Some, in a sense, graphene related stuff. And I'll begin with a little bit of a review of graphene. And from what I saw of the previous, of the level of sophistication of the previous talk, very interesting talk, by the way, this review would be completely unnecessary, except for I like to do it anyway, just to establish notation and to fix the thread of ideas. So please bear with me. So graphene, as everybody in the world by now knows, is a one atom thick layer of carbon atoms, which sit in a hexagonal lattice, like this cartoon from now famous review papers of already more than 10 years ago. So it has a hexagonal lattice. Hexagonal lattice is special in a way. I could tell you all sorts of ways in which it's special, but one of them is if you model graphene by a simple tight binding model. So what do I mean by that? I mean that you take a model where electrons like to sit at sites localized at each of the lattice points. And then in that model, the dynamics is simply the tunneling of electrons from site to site. So the Hamiltonian is written something like this as an operator which transports electrons from a site to any of the neighboring sites with a hopping amplitude, creation annihilation operators, and so on. This turns out to be actually a rather successful model of graphene in that it describes a lot, even though it's very simple, it describes a lot of the physics that's seen there. The hexagonal lattice is special and it's not a bipartite lattice. In a sense, it's a superposition of two lattices, which I've written here as black dots and white dots. And that's part of the special properties of it. Now, actually, a lattice gauge theorist would probably know immediately that the spectrum on this lattice is going to be relativistic. I don't really have time to explain that, but it's obvious in a way. But one can also just see it by direct computation, as is what's standard everywhere in the literature, and also by now in very old work and old review papers. And that's where you simply solve the Schrodinger equation, which is a simple linear difference operator together with a time derivative equation to find the energy spectrum. And it can be found, and it looks something like this. There are two bands. There's particle hole symmetry. So bands are reflection symmetric through this gray plane that's in the middle here. So there are positive and negative energy levels, so to speak. Also, the density of electrons in graphene are so that the lattice is exactly half filled. There's one valence electron per site, and 2 would fit. That means that the charge neutral material has its Fermi level right at the symmetry point, which is on this gray plane and happens to be where these two bands touch at discrete points. And these are the so-called K points of graphene, and they're what's responsible for the relativistic spectrum there. In fact, if we agree with each other that we'll only look at low energy phenomena here, small excitations near the Fermi level, we can impose a cutoff here. And then the excitation spectrum of the electrons that we're interested in for all the world looks like a Dirac cone. And in fact, looking at the details of the lattice Hamiltonian and how one finds that, one could see that for small momenta in the vicinity of these so-called K points, the lattice Hamiltonian actually can be made to look like a matrix Hamiltonian, which depends on derivatives or here wave numbers. And that matrix Hamiltonian looks just like the Dirac Hamiltonian of a three-dimensional fermion. Now, the degeneracy in this Hamiltonian, it's 4 by 4, but you can see that it's arranged into 2 by 2 blocks. It's 4 by 4 because there are actually 2 of these degeneracy points per Brillouin zone. So this, for particle physicists, is a famous fermion doubling, which should happen for a model with local interactions on a regular lattice. Then indeed here it does. And so you get doubled fermions, and what in graphene science is called 2 valleys. And the valleys you could sort of think of as the valleys in this energy landscape near the K and K prime points. The other cones here are simply related to these by reciprocal lattice translation, so they're not independent. Okay, so here is my Dirac Hamiltonian. I haven't put in the spin degree of freedom yet. I will in a moment. And notice that the 2 blocks look a little bit different, but rather simple relabeling of the components of, say, the spinners for the lower block, changing around, which in a sense is reconventioning what I mean by the components in terms of the sublattices, makes the 2 Hamiltonians look the same. And so you have a double degeneracy. For restore spin, that's double times 2 is a 4-fold degeneracy. So at least the naive weak coupling model of graphene would use this massless Dirac Hamiltonian as a Hamiltonian, would describe in a sense, the low energy excitations near the Fermi level by this Hamiltonian, with an additional 4-fold degeneracy, which looks like an SU4 flavor symmetry. This flavor symmetry and the massless nature of the Dirac electron probably came home to the condensed matter community, well, a long time ago, but the singular result that did that was the observation of the so-called anomalous quantum Hall effect. So this is an integer quantum Hall effect, and I've stolen this diagram from one of these 2 papers, which were published back-to-back in Nature, by the way, in 2005, which shows this. So this is an integer Hall effect, and you can see on this graph some very well-pronounced steps. In fact, the energy scales in graphene are so high that these steps are visible at room temperature. In fact, I think this insert in the top corner here, this thing is what this looks like at room temperature, where the steps are still visible. And this was, in a sense, anomalous, but really just a signature of the fact that the active electrons are massless in the following sense. Well, first of all, there's the SU4 symmetry, and that's seen in this picture because the height of these steps are actually 4 quanta of the integer quantum Hall effect. So that's the SU4 symmetry. In fact, the equation which describes the steps is down here, the Hall conductivity on the steps. The other thing is that this step here goes across zero density, the charge neutrality point. In other words, charge neutral graphene is halfway up a step, which, or in the middle of 2 steps, I should say, halfway in the middle. And that's unlike conventional semiconductors, where the neutral material either has everything filled or everything empty, and is a signature of massless Dirac electrons, because for massless electrons, there's a Landau level that sits right at the charge neutrality point, right at zero energy. And then the charge neutral graphene has that Landau level half filled. And so you should be in the middle of the step, and that's seen beautifully here. Of course, much more sophisticated things have been done since this, and for both the integer Hall effect and the fractional Hall effect has been observed, and there is a long story to be told here. But this was the one real signature that of massless fermions that caught everyone's attention. And so the moral of the story is that at least in some regimes, one can model graphene in this way, by 4 relativistic massless 2+1 dimensional fermions, a very simple quantum field theory, a relativistic quantum field theory with a Dirac Lagrangian like so. The Dirac matrices here are 2x2 matrices. That also has interesting consequences. And then there's this SU4 symmetry. And these, the fermions are massless. And so as a field theory, this at least naively has a scale symmetry, and not only a scale symmetry, but a conformal field theory. So this field theory actually should have the full 2+1 dimensional conformal symmetry to it. Now, of course, this might not be very realistic. In fact, just about any interactions one might dream up for these electrons, if they're important at all, are going to break some of these symmetries. Generally, they will ruin the relativistic invariance. For sure, the conformal symmetry. Also, they will tend to break scale invariance. So the real world could get quite messy. But on the other hand, if you look at what's seen, and this is also very old stuff, this is an ARPA's spectrum for the picture of the electron spectrum and graphene. You can see a cone there. And this is on a messy substrate. I think this is the old stuff on silicon dioxide still. But you can see in a fairly big dynamical regime, the spectrum really does look conical. Where it doesn't, well, there's sort of messy stuff at very long wavelengths, sort of up here. And then the band should start to curve a bit noticeably around an electron volt or so, which is a pretty high energy in condensed matter physics, right? That's about 10,000 degrees Kelvin. So thermally excited electrons are never going to know about this curvature of the band, but it should start to curve back around an electron volt. And I actually can't see the units here, but it might be an electron volt high. Here's another graph, which is a little bit newer. And this is from the Lanzera group in Berkeley. And here they're actually looking to study some predictions of a curvature in the Dirac band. which should happen at very low energies. So you can see this dimple shape down here. This is what they're looking for. That has been found in a sense. It is a prediction of perturbation theory using the Coulomb interaction. The Coulomb interaction is very strong in graphene if you simply sit down and start doing computations. The graphene fine structure constant is big. It's sort of larger than 1. So this perturbation theory is very poorly convergent and would seem like nonsense from the get-go. But these things have slowly over the years been checked by lattice calculations or non-perturbative lattice calculations. Whoops, that's not good. Okay, non-perturbative lattice calculations, and actually the perturbative computations have been vindicated to some extent. I'm not sure how that works really. A very badly converging asymptotic series still turns out to be well estimated by the kind of leading terms, which are already bigger than the 0th order terms. But anyway, it is there, but you can see in this work, I think the theoretical prediction, this red curve here is the red curve here, and the data is a dotted line that looks quite a bit straighter, even to the eyeball, than the theoretical prediction. And this really does, well, this is already in the low energy regime where you expect that some messy stuff might occur that, but you can see that the spectrum is still pretty straight. So to some approximation, graphene finds a way to be scale invariant in quite a large dynamical regime, at least scale invariant to a good approximation. I should say it's a little bit mysterious why, given all of the strong symmetry breaking interactions around. I'm not sure the final words on this subject are in yet, but one can just, for our purposes, perhaps take it as an experimental fact. Now, what I want to talk about is graphene with an edge. Well, of course, every piece of graphene in the world has edges to it. So this is something fairly generic, but what I mean by an edge is a fairly coherent edge. That's an edge that has the same structure all along it, like is drawn in these two diagrams. So for example, the first one is called the zigzag edge. The sheet of graphene is cut along an edge like that. And the second one is called an armchair edge. And there are actually all kinds of other edges one can make. There are bearded edges and so on, you know, things with the extra stuff hanging off of each of these and so on. I'm not going to worry about those here so much. Some of them have been explored, for example, cutting graphene at a slightly different angle that still looks like a zigzag edge with a bigger period. I think those angles are discrete. That's been discussed, and its continuum limit has been discussed, and is something fairly widely known in the literature. I'd say armchair edges are much less explored, and I will try to convince you that they're interesting for their own reasons. The zigzag edge was recognized to be interesting 10 years before graphene was discovered in the lab, actually, and there are literally thousands of research papers written about zigzag edge effects. So it's far from new that the armchair is relatively less explored. Okay, so what I want to do here is look at my model of graphene using relativistic massless fermions with an edge that is on a half plane. So the mathematical model I want to use is just this simple one, the massless Dirac equation. So I have a quantum field psi which satisfies that equation, and it lives on a half space, which I will take in all subsequent formulae to look like this. So it's cut along the y-axis in the xy plane. So the x coordinate goes from 0 to infinity, and then y and the time coordinate take their usual values on the entire real line. We can start by thinking about just a single species of fermions. So this is a two-component or two-dimensional representation of the SO21 Lorentz symmetry. So it's a spinner of that symmetry. And then I'll talk about putting back in the two valleys and the spins later on, which of course one would have to do to be realistic. But I find considering this relativistic fermion one at a time actually is pretty interesting because it's fairly anomalous. Okay, so we have this Dirac equation. Some of the interest here, interesting stuff comes because the Dirac matrices are 2 by 2. So they obey this rather special identity, which is special to 3 space-time dimensions. This last term doesn't happen in any other dimension, and that actually does lead to something interesting. Okay, so that's the Dirac equation. Of course, on a space of boundary, it needs to be supplemented with a boundary condition. And the appropriate boundary condition is the one that makes the Hamiltonian self-adjoint. And that said boundary condition is that the current normal to the boundary should vanish at the boundary so that particles aren't leaking out or into the system. And so whatever boundary condition one imposes, it should lead to this condition of vanishing current at the boundary. And one can easily find some nice linear boundary conditions that do that. In fact, here there's an infinite family of them, which are parameterized by an angle phi, which if imposed, all do the job. Now, the proper boundary condition should, in a sense, eliminate half of the components of the spinner at the boundary. One can see that just from counting of the number of equations that are contained in the Dirac equation, and this does that. Phi has to be an angle here so that, well, if you square this matrix that's in front of psi, you get, it's a projection operator, you get the matrix back. That's in a sense for consistency of the boundary condition. I'm not sure that this family of boundary conditions can actually be found from graphene. I haven't worked through the details. I might conjecture that if you chop the graphene sheet at some incommensurate angles, maybe somehow you find this boundary condition, and maybe one can realize some of these angles. As a field theory, this boundary condition is most interesting at its extreme ends, and those happen to be the ends where the boundary condition describes the armchair and zigzag boundaries of the graphene sheet. So when phi equals pi over 2 at one end, that describes the armchair boundary condition. This is actually just the usual boundary condition, right? Gamma 1 is a normal component of the gamma matrices. The usual boundary condition of the MIT bag model, or that's used a lot for fermions. I think it's used there because it preserves symmetries. With this boundary condition, this field equation actually describes a boundary conformal field theory. On the other hand, the boundary condition actually doesn't support edge states. That's similar to the fact that a carbon nanotube with armchair configuration is a gap spectrum for similar reasons. But this higher degree of space-time symmetry is still interesting, and we'll have a little discussion about that shortly. At the other end of the spectrum of boundary conditions is phi equals 0, that describes the zigzag edge of graphene. This boundary condition actually breaks Lorentz invariance, ruins the conformal symmetry, still scale invariant, translation invariant for translations along the boundary, translations in time, but a lot of the space-time symmetry goes away. However, it is still interesting in that the zigzag edge supports edge states. And this was noticed a long time ago in the mid-1990s, and there's been tons of discussion in the literature about it. And I'll tell you a little bit about what goes on. Of course, pulled up to my point of view. Okay, to study the first armchair boundary condition and to understand why it preserves conformal symmetry, one can write down the generators of conformal transformations, well, of the space-time translations, Lorentz transformation, scaling, and the conformal transformation. So the whole list, as they would act on the fermion field, are contained on this page. The reason why a boundary condition, like I discussed on the previous page, can mess up Lorentz invariance is because the boundary condition should commute with the action of the spin part of the Lorentz transformation generator. For the armchair edge, it does, but for the zigzag edge, it doesn't. So the transformation generated by this thing is no longer a symmetry for the zigzag edge. And then that also turns out to be true for these things. They also don't generate a symmetry of the zigzag edge, but they do generate a symmetry of the armchair edge. And so the armchair edge has all of these symmetries, preserves all of these symmetries, whereas the zigzag is less. Okay, so let's look at the armchair edge. So my argument is it's a simple example of a fermionic boundary conformal field theory. Here's the Lagrangian, here's the boundary condition. Well, this is simple, rather trivial free field theory. One can easily find the two-point function the Fermi field. It's the usual free field two-point function modified by the boundary condition. The modification from the boundary condition is just this image charge piece. And then one can go and compute some simple things. Well, this is free field theory. We expect things to be simple. This boundary condition violates parity and time reversal invariance, but it conserves charge conjugation. That means that you would expect that the current one-point function vanishes, and indeed it does, and also Lorentz invariance, for at least for part of this one-point function, would tell you that it vanishes. But these discrete symmetries, which would forbid a psi bar psi condensate, are actually broken by the boundary condition. And you could see there's a mass operator condensate in this theory that looks something like this. So here x is the distance from the boundary. So this condensate lives near the boundary and decays away like a power law, 1 over x squared. Of course, the power on x is simply dictated by the conformal dimension of the operator psi bar psi, which of course in free field theory is the same as the engineering dimension, which is 2. Okay, so this is very simple. One could perhaps ask a more complicated question. For example, there's a rather well-known result in usual boundary conformal field theory, which asks if you switch on a background electric or magnetic field or electromagnetic field, how does the system respond? What are the one-point functions? This famous result is due to McCavity and Osborne and looks something like this. So they did a heat kernel calculation actually it was just a scalar field theory in 4 dimensions, but the applicability of their results seems to be wider. And they show that if you switch on a constant electromagnetic field, which is summarized in this field tensor F mu nu, the component of F mu nu normal to the boundary, well, sorry, it's sort of normal. Here n is the normal to the boundary, so F mu nu contracted with a normal unit vector normal to the boundary is this quantity, that the expectation value of the U1 current in the theory should just be proportional to that thing. Let me clean it up a little here. Should simply be proportional to this combination of stuff times a power of 1 over the distance from the boundary. That power law is dictated by the dimensions of things. F mu nu always has dimension 2. In 3 dimensions, the current density has dimension 3, so it should go like 1 over x. When you're living, pardon me, in 4 dimensions, as dimension 3 should go like 1 over x. And indeed, it has a power of 1 over x, which is just enough to make this dimensionally consistent. So this is an interesting result. Quite interesting because it's linear in F. The reason why it's linear in F is because of conformal symmetry. You might think of making something, let's see, F mu nu has dimension 2. So nu F mu nu x squared, this thing squared, say, is Lorentz covariant, scale invariant, translation invariant for translations along the boundary, but it's not conformally invariant. So the conformal symmetry forbids any function of this quantity on the right-hand side of this equation, and in a sense results in this linear relationship. But it's quite fascinating that conformal symmetry simplifies things so much that you only have linear response. There's no possibility of having a nonlinear response. Okay, well, that's interesting. However, there's a puzzle if we want to pull this down from 4 to 3 dimensions. And that puzzle is the following. That there's this 1 over x to the d minus 3 in front. So if I said d equals 3, that goes away. And that would seem to mean that the influence of the boundary doesn't go away as you go away from the boundary. And there's something wrong with that. That would mean that somehow very far from the boundary in a sheet of graphene, you should still see some vestige of this current. In real graphene, there's some anomaly cancellation, so there'd have to be a valley current, but still, it has that rather nonsensical aspect to it. Well, if you look at the formula carefully, actually, there's a coefficient that I didn't write here. And that coefficient actually diverges at d equals 3. So there's also a singularity there, which should be subtracted. And you can subtract it. You can renormalize by adding a Siegel counter term to the current. But when you do that, the current gets an anomalous scaling dimension. And being a conserved current, it shouldn't. There are theorems against that. So that's also puzzling. So what happens? Well, to look a little bit closer at this, we decided to just study this directly in 3 dimensions because 3 dimensions is a little bit special. It's special because there's a tensor in 3 dimensions which transforms in a rather special way under Lorentz transformations and conformal transformations, and that's this 3-index Levi-Civita tensor. And indeed, it plays an interesting role here. So if we go down to 3 dimensions, The first actual interesting part about 3 dimensions is if we look at the theory on the edge, that is, we impose the boundary condition. With that boundary condition, because the Dirac matrices are 2 by 2, it turns out that the charge density, which is here, when evaluated at the edge, has to actually be equal to the current density along the edge. So in a sense, the boundary condition forces a boundary current to be chiral. And in fact, if the other component that's left out, the J1, which should vanish on the edge, but its derivative doesn't have to vanish, if its derivative did also vanish, then the boundary current travels like it would in a 2-dimensional conformal field theory as some sort of a dispersionless wave traveling at the speed of light along the boundary, and it's chiral. It only travels in one direction. So that's an interesting consequence just of the boundary condition. And that should be true even independently of the symmetries. So even if we introduce a background electric and magnetic field, which break the symmetries, this is just a consequence of the boundary condition itself. So to look at what happens to this equation, what we did is we actually solved the theory in a constant magnetic field. So that's completely standard, a little more complicated than looking at Landau levels on the plane, because the boundary condition in this case changes Landau levels significantly. They become Landau levels, normal ones, far away from the boundary, but as you approach the boundary, the Landau levels become dispersive and do have some interesting structure. Anyway, one can solve and just plug them in and calculate the boundary current. And what we get is something that looks like this. It's proportional to EB, the magnetic field. And this is, in this case, just N mu F mu 2 in a sense, where N mu is the unit vector in the space x1 direction. So this is just the same as this thing up here. But then there's a bit like this. So somehow in 2 dimensions, this particular combination of stuff is still conformally symmetric. Then that was a surprise, that just as you come down from 4 space-time dimensions to 3, somehow is discontinuous at 3 dimensions, and conformal symmetry is just a little bit weaker, and it allows this to be here. So our boundary current can be a function of this dimensionless combination of stuff. The coefficient I haven't written here because I don't actually know it in closed form. I have it as some summation of parabolic cylinder functions, which looks really messy, but I can prove that it isn't 0. And also I can prove that its derivative isn't 0, which means it really does depend on this stuff, which goes away as you go away from the surface. So I've solved the little quandary that at d equals 3, the above equation doesn't seem to damp, and that's because this Gaussian damping is actually allowed here. And then the chirality of the boundary current means that as you get closer and closer to the boundary, this actually becomes equal to the charge density that's induced by a magnetic field. So that's really interesting. It's a sort of a zero field Hall effect, but not the one that's usually talked about, the Haldane thing that one talks about in the context of graphene, where you have a Hall conductivity with 0 magnetic field. Here, instead, you put a magnetic field, but you don't need an electric field to induce a current. The current appears with 0 electric field. And I find that rather interesting. And of course, that's only allowed because of the reduced symmetry of this system, which violates charge conjugate, or pardon me, parity and time reversal symmetries. Okay, well, if you put in the other values actually in graphene, the other valley would have the opposite boundary condition. And in a sense, this effect cancels. It has anomaly cancellation. So the really interesting stuff here is either for, well, valley currents, which are maybe a little bit less physical than the U1 current, for sure less accessible, or perhaps for some valley polarized Dirac material, like is thought to occur on the boundaries of some topological insulators, in which case what I said here, well, would seem to hold. Okay, so let me check the time, and I think I have a little bit of time left. Let me jump over to the other kind of edge. So that's all I have to say about the armchair edge for now, but it is an interesting bit of science. And for example, one thing I would like to compute there and haven't computed are the boundary central charges, because they should, in a sense, characterize the boundary conformal field theory there. And there are other characteristics and things that could be said, which are things that can be said due to the conformal symmetry. Okay, so let me jump across to the one that isn't conformally symmetric, but is interesting. And that's the...
Can I ask a little short question?
Sure.
Yeah, it's about what you just described. Look like the chiral magnetic effect in 1+1 dimension. Is that similar to that? A current induced by a magnetic field?
Yeah, you have a good point, actually. It's similar, although I think of the chiral magnetic effect as, in a sense, a buildup of current. You know, it's sort of a time-dependent chiral charge density in a magnetic field, whereas this is just static. Like you put a magnetic field and there has to be a current there, which to a good approximation is even non-dispersive.
Mm-hmm. Okay, thanks.
Yeah. Okay, so zigzag edge is much more studied. The original work was by this group, and it inspired literally thousands of papers. I think their paper has 1,000+ citations. So this is a subject where we are not alone. The interesting thing about the zigzag edge is that it supports a rather strange kind of zero mode. So this is no longer a conformally symmetric system, but it is scale invariant. And it might seem weird to have a bound state which is scale invariant in a scale invariant theory. Clearly, the binding energy has to be 0, but you just wonder how the bound state can manage to have a square integrable wave function, for example, if there's no scale to tell the wave function how fast it should cut off. I think that was my first reaction to this subject. It looks very strange, but indeed there is. And what they look like, I've written on this page. So we go back to the valley and spin polarized case of just one 2-component Dirac fermion for now, with the zigzag edge boundary condition. If we had the 2 valleys, there'd be 2 boundary conditions, one for each valley, which are opposite. So this boundary condition violates C, it violates P, it violates T, violates all of the discrete space-time symmetries. The doubling, if you go to two valleys, actually restores them all because the valleys transform into each other under each of C, P, and T. And it also, to some extent, cancels anomalies here, but not everything, as I will discuss. In fact, maybe I should have already said, one of the really interesting things about these edge states, which was noticed actually way back in the first paper about them, at least the first paper I know about, is that they seem to like to align their spins. So the edge should be populated by a bunch of edge states. In that picture of a zigzag edge, there's basically one state for each zig. So each of those things that sticks out, there's one state sitting there, populated by an electron, and the spins of those electrons like to line up. So the edge is ferromagnetic. So this is seen by mean field theory arguments and later on density functional arguments and so on. And there's even a proof at the lattice level that the weakly coupled Hubbard model will have this sort of ferromagnetic edges. And of course, that's a proof for the full graphene picture with two valleys and two spins. So there is something anomalous that one might expect. But from our own point of view, how would that come about? Well, let's start by looking at what the edge state looks like. So what we're going to do is we're going to study this material at very low energies, where we only have to worry about the edge states. We assume that we're close to the ground state. So all of the negative energy levels are filled, positive energy levels are empty, and we're simply talking about how electrons want to populate the edge states. Okay, so here's a massless Dirac Hamiltonian. I want to look for zero energy modes. That means static things. So you can kill the time derivative here and here. And then you see that these are something like d by dz bar, derivatives by complex coordinates on the two-dimensional plane. And so you can easily find these sort of chiral solutions of the above equation, which depend only on x plus iy or x minus iy in the appropriate place in the spinner. And then in this notation where gamma 0 is diagonal, my boundary condition says either the upper component or the lower component of the spinner has to be 0 at the edge. So this is an easy one to impose. So let me say this boundary condition tells me the lower component of the spinner has to be 0. That means that there are my edge solutions. These are bound states at the edge. How do you get a bound state without a scale? Well, what happens is you have a momentum that this wave function has along the edge. And that momentum, of course, is dimensionful, and it provides a scale, and then just the holomorphicity of this thing, and the fact that it should be an exponential and need the IKY to be a momentum eigenstate for the translation symmetry along the edge, gives you something exponential, which then, if you choose k to be less than 0, is actually normalizable. Right? The y integral is continuum normalizable because usual delta function for momenta, and the x integral dies off exponentially as x increases when k is negative, and so it's also normalizable. So there's how you get a bound state without any scale. In a sense, you generate a scale from other quantum numbers and use it to make your bound state normalizable. Okay, well, I find that interesting already. What else can one say about this? Well, I'm interested in the symmetries. I still have translation symmetry in time and along the y direction. And this certainly carries a representation, these states of those symmetries. In time, it's trivial because it's just time independent. Along the y direction, it changes by a phase, which is governed by k. So in a sense, K is the momentum carried by this state. What about scaling? Well, if I do a scaling transformation, I should scale X and Y by something. That can be compensated here by scaling K. And then actually the root K in front gives the proper scaling of the spinner too. So this works out nicely. These are not scale symmetric, but scaling of X and Y can just be compensated by scaling K. Okay, so if I have this extremely polarized graphene and I want to make a material, I should choose, I should discuss how the edge states are going to be populated. The spectrum of positive and negative energy modes here turns out to be symmetric. For reasons I don't entirely understand, I just solved it and I can see that it's symmetric and the density of states is symmetric. So that tells me that if I want a charge neutral material, half of these edge states have to be occupied and half of them have to be empty. To have half of them occupied would seem incompatible with two things. One is scale symmetry. In fact, the only way I can occupy these edge states that will be scale symmetric, since each state itself isn't scale symmetric, is if I occupy all of them, because then I have an entire orbit of the scaling transformation, or if I occupy none of them. Those two extreme cases. Those are both charged. So those both have a constant charge density. If I occupy all of them, I also would seem to have a huge momentum. Since K always has the same sign, there's no way to make a Slater determinant, for example, out of wave functions like this, which is independent of Y. So it's difficult to make a translation invariant state unless I occupy none of them. So this has that weirdness that charge neutrality, translation invariance, and scale invariance seem to be at odds. There isn't a way to get all three. I can get 2 out of 3, scale and translation invariance, by making the state highly charged. It doesn't mean that the material wouldn't find some other way, but it would seem like it breaks some of these symmetries, whatever state one would choose. Of course, if I add the other valley, that fixes things up. So let me add the other valley, which is this wave function down here. So now, for example, all of the momenta are positive. So if I symmetrize the populations of the two valleys, I could get a translation invariant state. If I want to be scale invariant, I still have to populate either all or none of the states in one valley. To be scale invariant and translation invariant, that means in both valleys, I should populate everything, or I should populate none. Those are both highly charged. In a sense, both valleys contain a large U1 charge. In one case, in a system which should be half filled, it's completely filled, and in the other case, it's completely empty. Should be half filled to be charge neutral. That's interesting for the following reason. I would say that if I, for some reason, required scale invariance and required translation invariance, and I might have good reasons for requiring translation invariance. Scale invariance, I'm not sure. I don't know a physical principle that tells me you have to have scale invariance here. But if I required it, my conclusion would be that I have a very large charge. My states of interest have a very large charge, either positive or negative, and I can't get around that. Well, that's interesting because now if I add the other spin as well as these two valleys, I could make something charge neutral by giving the other spin state the opposite charge. Then the charges of the two spin halves add up to 0. But that would mean that one set of spin states is completely filled, the other set of spin states is completely empty. In other words, it has a very large spin polarization or is ferromagnetic. So this is a symmetry argument, which tells you that if the system for some reason wants to be scale invariant and translation invariant, it also likes to be ferromagnetic, which seems rather consistent with all the predictions, although the other predictions are based on interactions, not just on symmetry. This ferromagnetism of graphene edges, I think, has been observed, but only rather recently. And I don't actually understand the papers well enough to know how reliably, if it's the result that's really there and should be thought of as a generic feature or not. But in a sense here, symmetries are predicting ferromagnetism. Okay, so that I've talked about here on this page, say. So here I've taken spin up, which is the right-hand column, the two valleys on the right, spin down, the two valleys on the left, and just repeated the argument that either these should both, this and this should both be completely filled, these completely empty to get charge neutrality, or vice versa, and those both give a big spin polarization. There's another possibility, and that's that this one's completely filled and this one's completely filled. That will cancel out the translation non-invariance. It gives scale invariance, and then these two, the other one should be completely empty. So there's in a sense, a crossed way of doing that. But that actually just puts the ferromagnetic order parameter in a different direction. It's still ferromagnetic, and I guess to convince yourself of that, you can just see that it's not invariant under spin rotation. So in a sense, it has to have a spin. Okay, so I've used up my time here. I should say that there is a little more you can do with that. You can play a little bit with degenerate perturbation theory and weak interactions. And one can actually show it's kind of a Hundrule argument, but this has already been done at the lattice level by Affleck and collaborators and people before. Then one can actually prove that in perturbation theory, this kind of ferromagnetic ground state, if you have a charge density interaction, is actually an eigenstate of the charge density. It's a Hundrule-like argument in that there's just no space to create particle-hole pairs when you organize things this way. So it kills the exchange interaction completely. And the direct interaction is also killed by charge neutrality. That then if the Hamiltonian is a positive quantity and you found a 0 of it, you actually found a ground state. So one can actually show that this ground state not only is the one that somehow one came to using our intuition about how symmetry should be realized, but also actually is the ground state of some weakly interacting versions of this model. Okay, and with that, I believe I've used up my time, maybe my time plus. So I come to my conclusions, and my conclusions are more or less what I have said already. So I'm looking at the Dirac equation in 2+1 dimensions on a half space. Studied the possible boundary conditions there, and there's a big array of them, and two special ones at the endpoints of the array that are perhaps more interesting than the rest. These boundary conditions, they actually violate discrete space-time symmetries. The two endpoints of the array are the boundary conditions corresponding to the armchair and zigzag edges of graphene. The armchair violates parity and time reversal invariance. The zigzag edge violates everything, charge conjugation, parity, and time reversal. And then we looked at some of the consequences to these. For example, some interesting induced currents in the armchair case. And what I've shown you is really just the beginning of such calculations. I believe there are several more interesting things that can be done that we simply haven't gotten around to yet. And then there's much better known and more widely studied zigzag boundary condition as edge states. And the only thing brought to that science, which is already very well established, was in a sense this intuition of wanting to look for a scale symmetric edge state in a scale symmetric theory, and found that that leads to ferromagnetism, which has already been suggested by looking at interactions. So completely different, well, putatively completely different point of view, and maybe is observed. And with that, I will thank you for your attention.
Okay, thank you, Professor. And I think we have time for a few questions. So, if there are questions, please raise your hand, or you can speak directly. Okay, while people come up with questions, I have a question. So so if you're looking for, well, systems which are scale invariant or are usually in sort of a phase transition, right? They're usually very sensitive to perturbations, whereas graphene usually, as the little I understand about it, has topological properties which are supposed to be stable under perturbation. So how can you make compatible these 2 points of view?
Well, actually, it depends on exactly what aspect you're talking about. The edge state story, for example, of course, the population of edge states should be extremely sensitive to perturbations, because any tiny perturbation that likes one population better than another will, of course, change things a lot.
Okay.
But the other aspect of graphene, the conformal symmetry, it's true, that would seem to be broken by almost every interaction. So number one, perhaps it's approximate, and the interactions just aren't strong enough to have a visible effect. Or maybe they do have a visible effect, it's just that there's a, if you back off your resolution, you don't see it. Or maybe graphene finds some way to make itself scale invariant. A renormalization group fixed point idea. It's a little bit hard to study analytically because the Coulomb interaction, for example, is probably the most important interaction there, is strong. So perturbation theory tends to be poor. Has been studied numerically, but critical behavior in numerics is actually not that easy to get a handle on.
Yeah.
So I would say that part of the science is still open. Does the question, does graphene find a way to make itself scale invariant?
Okay.
More scale invariant than you would expect.
Okay, perfect, thank you. And I think Professor Chernodub had a question.
There is another.
Gordon, good morning. I wanted to ask, just not actually to ask, just to make a comment, because I just gave a talk on quite there was some very small part which is close to your talk, and it's not about graphene, but it's about system which is one order, one dimension up. So if we consider this, can you please show page 15 of your talk? Just a comment, because you studied graphene.
You have to tell me when to stop because.
That's about Makevich-Osborne.
Oh,
I
okay.
think it's a little bit before. No, before a little bit. Yeah, here. Yeah. So no, just 15, a little bit down. Oh yeah, here. Yes. This one. So here D is considered to be, I mean, total dimension. So it's time plus space.
Right.
And if you work, yeah. So, and that's why in 3 dimensions, I mean, in 2 plus 1, basically, then you have kind of smooth behavior. But if you work in 3 plus 1, then just a comment, you know, it's because you were talking about 2 plus 1 dimensions, and I would like to clarify also for other participants, because when we have 3 plus 1 dimensions, then we have an explosion of current when we move the boundary. And then this coefficient in front of that is given not by topology, it's not given by topological properties, but it's given just by beta function. As you say that we have interactions in the system that we will get immediately some beta functions, and we should get their current will be non-topological proportional to beta function. And since the boundary is 2-dimensional, we don't expect any chirality there. For example, that effect is visible also in scalar QED. So in that sense, it's very interesting that in 2 plus 1, you get some topology there. And it's actually, yeah, it's reasonable. And it's very interesting to see if there is some connection with the higher dimensional theories. Don't you have any comment on that?
I'm not sure I have. This formula, I actually still don't understand what happens in their derivation that messes this formula up in D equals 3. It would seem that D equals 3 things are discontinuous because another conformally invariant combination of things appears there. But somehow D equals 3 is very special. D equals 4, I think the formula is fine. And it has a 1 over x in front.
Yes.
And the exponent on x is controlled by the conformal dimension of the operator. Well, actually a comparison of the conformal dimension of f and the operator. So it's true. In that sense, it's controlled by the beta function because the conformal dimension of f mu nu is. So I guess I'm just agreeing with what you said.
Okay. I just interested because we checked it in, I didn't believe this formula, by the way, when I saw it first time, and I decided to kind of to kill it, just making the simulation, first principle simulation in scalar QED on the lattice, because the fermions on lattice are difficult. Then we studied with the scalar QED, and we instead of killing it, we confirmed it. So it works in 3 plus 1. So I mean, when D is equal to 4. But in D equal to 3, we don't have it. And I must say that there is another comment that you see, I don't expect it in graph. Okay, I would say that in graphene, it should be really very special because in this beta function should be the beta function associated with the normalization of charge. But we know that in graphene, we don't have a normalization of charge. We have running of Fermi velocity, but not of charge.
Yeah, I know. That's why.
Should be really special.
That's why I think the coefficient, if this were applicable there, would have to be a constant. It's just dimensional analysis. And then a constant is a bit of a nonsensical equation because it means the boundary has influence infinitely far away.
Mm-hmm. Yeah. It would be strange a little bit. Okay, anyway, one should check numerically maybe. Okay, thank you very much.
Yeah.
Are there any more questions? No. I just had a quick question, or I mean, you know, these days with fashionable topics. So with the twistor Weyl graphene, I was thinking when you mentioned the that you had superconductivity because you have charge conjugation with the, I think it was the armchair boundary condition. But I guess that if you vary the angles, you probably also vary the boundary conditions, right there, maybe. So maybe that family that you were looking at could possibly, twisted bilayer, could there be a realization, or is it sort of very
It
different?
could be, although the twists, I think, are in a sense quantized to get bigger superlattices, whereas
okay.
the parameter in the boundary condition is just
It's
continuous.
Okay. Oh, I see.
So I'm not sure. I think that various cuts at various angles were discussed in a paper that's a very well cited paper by Akamerov and Bienecker already almost 10 years ago. But it seemed like there, if you cut graphene at any angle that still looks like a zigzag edge in a sense, just the zigs and the zags are farther apart, you still get the zigzag boundary condition. Like the continuum theory doesn't notice that the edge states are more sparse, since there's no scale to measure their sparseness.
Okay.
The things in between, I would conjecture that the incommensurate angles might be the boundary conditions in between, but I have never actually confirmed that. It might not be that difficult an exercise. It's all linear physics, but.
Okay. Thanks. We have another question from Mauro Cambiaso. If you can turn on your microphone.
Okay, thank you very much. So indeed, my question, I think it's related to your question, Daniel, because regarding this restoring of some discrete violated symmetries, the twisting could enhance some other, for example, crystalline symmetries, or also restore some broken ones. I don't know if that makes sense, actually, but it's a doubt.
Yeah, this I don't know, really. I think it depends on the details. First of all, I'm not completely sure if you take a twisted bilayer graphene and cut it, what the boundary condition will be. If you cut it so it's a zigzag edge for both, well, that might be, well, it might not be. It might depend on the twist. But I think that it could very well depend on the details, which is also interesting because then there are lots of possibilities and maybe some of them very interesting phenomena. But the answer, I don't know off the top of my head. I can't really tell you.
Okay, thanks.
Okay, so let's thank again Professor Semenoff for a very interesting talk, and we'll reconvene at 1 p.m. Mexico time.